All right, so I promised you that on Monday and Tuesday you would be going over all the other basic derivative rules. Okay, don't kill me. On the screen I just tried to put out all of the rules in layman's terms, plus their actual formulas mathematically. Now the power rule and the product rule, the first two on the screen, you've already done those before. Okay, I do want to introduce a little bit new notation. So far we've been using the prime mark, f prime of x, to denote the derivative. However, that's only one way to show the derivative. We haven't talked about it a lot this year, not lately anyway. The calculus was actually developed by two totally different mathematicians at the same time. It was actually developed by Newton and a guy named Leibniz that you've probably never heard of before, around the same time. And the notation we've used so far has been the notation that Newton used. He used y prime to denote the derivative of y, or f prime of x. He's also the guy that decided that the second, third, fourth derivative should be 2, 3, and then after that, you know, that was just too hard to do the rest, so we'd like 4, 5, 6. Okay? So that's all thanks to Newton. Leibniz, I believe, was German, and he developed this notation. And this is the derivative with respect to x. And there was this big controversy about, they thought that Leibniz copied Newton's work and vice versa, and it was a really big deal back in the day. Since then, we pretty much think that the need for calculus arose at the same point in time, and things developed on their own for both mathematicians, but who knows. But we're stuck with both people's notation. Some people like Newton, and they use his. Some people like Leibniz, and they use his notation. Honestly, they both have their uses. Sometimes it's easier to write with prime notation, f prime of x, but sometimes it's easier just to say the derivative of one particular function with respect to x. So d dx, d over dx, sometimes it's just easier. And in this case, if I'm writing out all the rules like this, it's a lot easier for me to use Leibniz notation. So the derivative with respect to x of any function that's of this form, ax to the n power, can be found using the power rule, which says that you can compute the derivative by multiplying the function by the exponent and reducing the exponent by 1. So this is what Blair told us last week. Move n out in front, n times a, and then reduce the exponent by 1. The product rule we talked about on Thursday. Given the product of two functions, you can compute the derivative by taking the derivative of the first function times the second, plus the derivative of the second function times the first. So the derivative with respect to x of the product of two functions is equal to the derivative of the first times the second, plus derivative of the second times the first. Now, we're going to look at two new rules today, the quotient rule and the chain rule. The quotient rule is for if you're taking the derivative of the quotient of two functions, f of x divided by g of x. Here's how it works. Given the quotient of two functions, you can compute the derivative by taking the derivative of the top function times the bottom function, sound familiar, minus the derivative of the bottom function times the top function, all divided by the bottom function squared. So it's going to look like this, derivative of the top times the bottom, minus derivative of the bottom times the top, all divided by the bottom function squared. Okay. So I'm going to show you some examples in a second of how this works. We're also going to go over the chain rule today, which means that given a function with within another function, you can compute the derivative by doing the normal derivative of the given function times the derivative of the inside. Kind of hard to write out into words, but here's what it looks like. d dx of f of g of x. Notice g of x is plugged into the function f of x. So I'm going to compute the normal derivative like normal, but then I've got to remember that g of x is a function inside of f of x, and so I've got to multiply by the derivative of g of x to get the full derivative in here. I'll show you an example of how this works in a second. It'll make a lot more sense. Okay, let's look at an example of the quotient rule first, and then we'll look at the chain rule. Okay, let's compute the derivative of x squared plus 3 all divided by 2x. Okay, so in order to compute the derivative, I'm going to have to use the quotient rule here. And so I'm going to do the derivative of the top times the bottom minus derivative of the bottom times the top, all divided by the bottom squared. Derivative of the top would be 2x times the bottom minus derivative of the bottom, which is just 2, times the top, all divided by the bottom function squared. So all is 2x squared. I'm going to clean this up a little bit. 2x times 2x is 4x squared. Minus, distribute the 2. It'll be minus 2x squared minus 6, all divided by 4x squared. Combine like terms. This will be equal to 4x squared minus 2x squared is 2x squared minus 6 all over 4x squared. I can factor out a 2 on the top and bottom to simplify a little bit. 2 cancel. X squared minus 3 over 2x squared. Okay, look at the next example. Try it on your own using the last example as a model. Talk with people in your group after you've tried it on your own. See if you got the same thing. See if you can get the right answer before I go over it in the video. Pause here. Okay, so let's find the derivative. Derivative of the top would be 12x squared times the bottom minus derivative of the bottom, which is just 1, times the top, all divided by the bottom function squared, so x plus 1 all squared. Cleaning things up a little bit, I'm going to distribute in the top to get 12x cubed plus 12x squared. Distribute here, that'll be minus 4x cubed. All divided by the bottom squared. I don't think it's worth my while to multiply that out. I don't think anything's going to cancel, so I'm just going to leave it like this. Combine like terms, 12x cubed minus 4x cubed would be 8x cubed plus 12x squared all over x plus 1 squared. I can't really simplify beyond that, so that's my final answer. But the quotient rule is not too bad. Let me tell you what people mess up on. People mess up by forgetting that it's subtraction of the two things, derivative of the top times the bottom minus derivative of the bottom times the top. And believe it or not, the easiest part of the problem is just squaring the denominator. But we get so involved in taking derivatives in the numerator that we forget to even put the denominator sometimes. So be really careful about those two parts. Okay, so the chain rule. Remember what the chain rule said. It's a function plugged into another function. This is your composite. So take the original derivative like it looks, but don't forget that there was a function plugged into the middle. You need to multiply by the derivative of it as well. Here's what it looks like. Compute the derivative of this. Now this is a basic example. I want you to see how the chain rule works. You could obviously square this binomial, and yeah, you could do it the old school way. But let's see how the chain rule would apply to this one, so that whenever we get to more complex things, we'll know what we're doing. Okay, so compute the derivative like normal. So this looks like the power rule. So move the 2 out in front and reduce the exponent by 1. Now, 2x plus 1 is the function inside of the other function. So I've got to multiply by the derivative of the inside. So I need to multiply by the derivative of this part. This is the inside. So the derivative of 2x plus 1 is just 2. Anything to the first power, that's just that. And so just to clean up, 2 times 2 is 4x plus 2, all times 2, which would be 8x plus 4. You can do that several different ways, but make sure you get 8x plus 4. Now you should see that if you actually square this binomial and take the derivative using other methods, you should still get the same answer. Okay, but how does that apply to a more complicated example? Remember from Thursday, we can rewrite this as 2x plus 1 to the 1/2 power. Everybody's favorite power rule to do. So I'm going to do the power rule like normal, but remember that 2x plus 1 is the inside of the function. So I need to multiply by the derivative of the inside at the end. Move the exponent out in front, 1/2 of 2x plus 1. Reduce the exponent by 1, so now it's to the negative 1/2. And I need to multiply by the derivative of the inside, so times 2. As I start to clean this up, I notice that 1/2 times 2 is just 1, so these things will cancel since all 3 of these are just products. And so I've got 2x plus 1 to the negative 1/2. I don't like negative exponents in my answer, so really this is 1 over the square root of 2x plus 1. I'm going to come over here and get some more work. If you don't like this, then multiply, rationalize your denominator. So the square root of 2x plus 1 all over 2x plus 1 would be your final answer. Okay? Now, we know a lot of different rules for taking the derivative of functions. Obviously, we've been using pretty much one rule at a time, but you can have problems where you have to compute the derivative with several of these rules all mixed together. Let me show you a couple of examples, and on your homework there's a couple like this as well, so be careful. Compute the derivative of 4x over x plus 2 all squared. Now, you should see that there's 2 different rules you're going to have to apply. Obviously the quotient rule, but as you're evaluating the derivative of the bottom, you're going to have to apply the chain rule. Now, which in this case is not going to really affect it much, so let me actually make this better. Let's do 3x plus 2 all squared. That'll make our problem more interesting. Okay, so I'm going to start off with the overall rule being the quotient rule, and then be careful when you compute the derivative of the bottom here. Okay? In fact, why don't you go ahead and try it? Try it on your own first. Really work with your group, see if you can all come to the same conclusion, and then unpause the video and listen to my explanation of it. Okay, so derivative of the top is 4. times the bottom minus derivative of the bottom. Now be careful here. The derivative of the bottom is the chain rule, 2 times 3x plus 2 to the first power times the derivative of the inside. This is inside. Derivative of 3x plus 2 is just 3. This whole thing is the derivative of the bottom times the top. Now that was inside the quotient rule. Remember, I'm working in the quotient rule, so don't forget it's all over the bottom squared. So 3x plus 2 squared, squared. Okay, so I'm going to simplify. In the top, let's see what's going on here. Be strategic about this. Don't kill yourself simplifying these. Notice you've got 3x plus 2, 3x plus 2, 3x plus 2. So we want to kind of leave it so we can factor out and cancel some of those. So I'm going to leave 4 times 3x plus 2 squared minus, here 4x gets multiplied by everything. 4x gets multiplied by the first term. Well, it's all just multiplied, isn't it? Okay, so 4x gets multiplied by all this. 2 times this function times 3 times 4x. So just the 2 times 3 times 4x can kind of all be put together. So that's 6 times 4, 24. X times 3x plus 2. All over, and squared would be the 4th power. So 3x plus 2 to the 4th power. So notice you've got some things that can cancel. If you factor out 3x plus 2 on the top and the bottom, then this will just change to the 1st power. This one will completely cancel out, and the 4 will change to the 3. So if I distribute the 4, I'll have 12x plus 8 minus 24x all over 3x plus 2 to the 3rd. Come on, like terms, 12x minus 24x is negative 12x plus 8 over 3x plus 2 all cubed. So this would be your final answer. Okay. So it might be worth taking some of the problems from the notes and reworking them a couple of times to make sure you've got these examples down before you do the rest of your worksheet. On your worksheet, you need to complete 7 through 16, keeping in mind that in some of those problems you do have several different rules all in one. Okay, so try them on your own, but if you need to partner up with somebody, that's going to be okay. You guys are really good about doing your own work. Have all the way through the end of that worksheet done by Wednesday. We'll be going over them, we'll be discussing them. If something seems way too crazy to simplify, you can just leave it for now and we'll talk about it on Wednesday. But go ahead and try your best to apply these rules. The rules are the main important part of this, not killing yourself on simplifying crazy functions. Okay? You do obviously need to be able to simplify something like, you know, the last example we did, that shouldn't be anything that's beyond you. But when it comes to all of the crazy rational exponents and things like that, if you get totally lost, don't freak out. Be able to apply the rules that we've discussed. That's the big part. Okay, we can work on the simplifying part later. Okay. Good luck. And you can post questions on Edmodo if you would like. I'll be checking that. But I think you'll be fine. Have fun.